Okay. So this second concept in collage is just about electric field diagrams and how those work. So hopefully you've now watched the first part, the video on the first part of like how to calculate an electric field and like what is an electric field and how is it related to force. And I walked through some examples in the first video. This video is really just gonna and go over sort of like what an electric field diagram looks like. So I linked this to this concept on electric field diagrams, this simulation. So if you click here, it's weird the link disappears, but you should still be able to click it, and then this comes up. This is a simulation made by the University of Colorado. They make these they call them PhET simulations, and they're in my opinion, excellent in terms of visualizing things that are sometimes complicated to visualize in physics. So yeah, like an electric field line diagram is essentially just a visualization tool that helps us understand the geometry and how the electric field behaves in space and basically the shape of it. So the way that this simulation works is you've got this like sort of blank space here, and then you can pull charges up into the space and you can see what the electric field looks like. Okay, so like let's just go through some of these points here. So each arrow represents both the direction and the magnitude of the field at that location. So the convention says um, that the lines originate on positive charges or infinity. So we'll talk about the infinity stuff in a second, but positive charges. So I've put like here, I put a positive charge in space, and you see that all of the field lines originate at the positive field. If I put a negative charge, you'll notice that all of the field lines point towards the negative charge. So that's what this point means, like lines originate on the positive charge or infinity. This would be like an example where like these lines are originating like so far in space, like so far away that we just call it like infinitely far. Like it's some like indeterminate amount of distance that's like so far that it might as well be infinity. Okay, so like these field lines are coming from like some infinitely far off point, and they're terminating on the negative charge. Okay, and then if I put a positive charge, we would say the field lines originate at the positive charge and they go towards infinity. Okay, so that's like the direction convention. The number of field lines is proportional to the magnitude of the charge. So the more densely packed the field lines are, the stronger the charge is. You can kind of see this in the simulation by like stacking multiple charges on top of each other here. You see like the field lines become denser and denser as I do that. I mean, sort of. The visualization only works to a certain extent, but you sort of see the idea. Like the field lines are denser, the more the stronger the charge. So that's one thing. I mean, you should play around with this. It's very fun, and I think it's a great visualization tool. If you put like a distribution of charges, like I did in the first example, you see the field is like, I mean, it's complicated, right? Like it bends, like as a result, especially if there's sort of an uneven distribution. Like if I put, stronger over here, it's going to affect like the field in the space surrounding the vicinity of the charges. Um, okay, so that is pretty much, well, let's just go through a couple of these other points. So the closer you are to the charge, the stronger the field is. Okay, and just like we saw with the math in the first part, it's a 1 over r squared relationship. So like if I compared the field here close to this, to these two charges, if I compared the field here to like, some distance r out here, like the distance, the difference in the field magnitude would be like 1 over r squared. It would be weaker, like way, way weaker, like exponentially weaker over here. Okay. Another thing you'll notice is that the field lines never cross. Okay, like they'll always like start at a positive charge and they'll either end at a negative charge. Let's see what that looks like, because that's relevant to like the dipole conversation that is in the last section of this chapter is when you have a positive charge, and is that just one positive charge? Yeah, and then I put kind of close in the vicinity a negative charge. This is an electric dipole. Okay, so this is what I talk about in the last section. So some things to notice about the electric dipole is the field lines start on the positive charge, and most of them like end on the negative charge. Right, so like they sweep around. You can imagine like connecting all of these arrows into like lines. I mean, this one obviously doesn't. It goes off in infinity, and this one here comes from infinity. But like, the field lines start on the positive charge and end on the negative charge. Um, and I mean, I think another thing that's good to point out is that the field lines represent the direction that a positive test charge would move. So it's like the direction of the force, right? So if I put like a little positive test charge right here on this spot, the force at that point in space would be in the direction that that vector is pointing. And I think that's pretty much it. I mean, like I encourage you to go through and read. I mean, this isn't a very long section. Just read through this and look at the pictures, and it gives you like a sense. Oh, here's the dipole drawn out. And this is sort of a prelude, this field line density. The number of field lines that go through like a given area, that's something called electric flux, which is something that we'll be dealing with this week in the tutorial. Okay, it's very short, but I just wanted you to see this, and it's a very useful tool, and I hope you play around with it.